Okay, so let's move into the worksheet number 10 from lecture number 10. So lecture number 10 is a long lecture. Make sure that you watch the lecture very carefully because it's everything is drawing and a lot of things are there, very dense lecture. Try to review it probably a couple of times. Okay, so mainly in lecture number 10, what we discuss is the reflection and refraction. So reflection and refraction. So we discussed about reflection law, refraction law. Simple example that you can think is by drawing a boundary of some two materials. We'll say I have air and I have glass, right? So when you send the light to this media, what will happen is, this is, we call it as incident light, right? Incident. So now this light will reflect back to the same media, that we call it as the reflection. Some of the light will go through the media, that is, we call it as refraction. Refraction, right? So now angle that we label here, I'm going to label this angle is theta incident. This angle is theta 1. This angle is theta 2, right? So now what the reflection law is saying to you, reflection law is saying here, your theta incident should be equal to theta reflection if you measure with respect to the normal. That is, we call it as reflection law, very simple. So that will happen in mirrors. Yes, here. So refraction happen in mirrors. Under that, we discuss about the plane mirror. We discuss about the concave mirror. We discuss about the convex mirrors. Right? This all happen in this reflection law. That means incident angle equal to reflection angle. So now refraction is not that simple. Refraction law, we call it as Snell law, Snell's law, right? So now this law is saying that if you take the media in air over in glass, N is in S, N is, we call it as refractive index, right? So what that basically means is, this is giving the ratio or speed of light to the speed of light inside the media. So in speed of light in the vacuum divided by speed of light in the media, we call it as the refractive index. And this number is always greater than 1 because the speed of light is always greater than the speed of the light inside any media, right? So now Snell's law saying that if you take the, in here I have air in the incident media times the sine of incident angle is equal to second media, in this case I have glass, times sine of theta 2. These all the angles measured with respect to normal line. So now this law, we use it for lenses, right? So we use for the converging lens and also diverging lenses. Right? So now this is the rules that we are following, but when you go to these mirrors and lenses, you have a formula that you can theoretically calculate or theoretically locate the image location. So we use this formula, we call it as lens formula and also as mirror formula. Di d naught equal 1 over f. Di is the distance from mirror or lens to the image. D naught is the distance from mirror or lens to the object, and f we call it as focal point. F will be equal to radius divided by 2. Radius is the, if it is a circle, that will be the radius, and if it is a plane mirror, your f will be basically infinite. There is no value for the plane mirror. So we discuss those things. In addition to that, we write the magnification by using di over d naught, and also this will be equal to height of the image divided by height of the object, right? Those are the formulas that we use for image location, to find the image location in lenses and also for the mirrors. The same equation, same formulas. Those all have very important information. When the virtual image is one thing that you need to know. When you say virtual means basically there is no real lights. That's what virtual means, right? No real light. That means you create the image without real light intersection. So these are virtual, right? Basically your di will be negative if it is a virtual image. Negative for virtual image, right? So real image, it will be positive. In addition to that, M give you the information about the orientation of the image. If your image is inverted, then your M will be negative. So negative give you inverted image. Inverted from the object, okay? It will be opposite direction of the object orientation, inverted image, right? So we learn those informations. We're going to do those problems by using those concepts. Okay, so now my first problem is just understanding of reflection and refraction according to the given media in this problem, right? So now let's see what I have it in here. So you see that I have N1 and N2, and I have angle incident theta 1 given 50 angle, given 50 is not the angle I need. So I need the angle with respect to the normal, that will be 40 degrees, right? So now this one we know it is 40. And I'm talking about the first diagram. So now N1 and N2 are given in the question, and beam is 50 with interface. Now part A. So what is the angle of reflection at point A? So that is theta 1 prime. So that will be how much? 40 degrees, because reflection will be same as incident angle, right? And what is the angle of refraction at point A? So now I need to find the refraction at point A. So I need to use Snell's law. N1 sine theta 1 is equal N2 sine of theta 2. Theta 2 is the one I need to find it out. Because of that, I can write the theta 2 from here by using divide by N2 first. N1 divide by N2, and we have sine of theta 1. Let me write sine theta 2 first. And then from this, you will be able to write the theta 2 by taking sine inverse of this value, N1 over N2 times sine of theta 1. Okay. So you can calculate it. Theta 2 is equal sine inverse N1 over N2 is 1.33 divided by 1.77 times sine 40 degrees. Give you the theta 2 angle. What I know is, since your N2 is greater, it is bending towards the normal, that means theta 2 value should be less than 40. Okay, what I get is 29 degrees. Okay, that is part A. Let's move into the part B. In part B, what is the angle of reflection at point B? So now point B here, right? So this is theta 2. Now it's asking the reflection angle theta 2 prime. Everybody know that this theta 2 prime is equal to theta 2 that we just found, 29 degrees. And next part, what is the angle of refraction into the air at the point B, where air have refractive index 1. So now we're going to write the Snell law at point B by taking N2 of sine incident to the air media will be theta 2 should be equal N3 times sine of theta 3. So what we are looking for is theta 3. As you know that you can write theta 3 equal sine inverse N2 over N3 times sine of theta 2, and that will be equal sine inverse N2 over N1. N2 in this case is 1.77 and N3 is 1, right? And then sine of 29. So that will give you the theta 3 angle. What you know by compare to the theta 3 compare to theta 2, that means compare 22, theta 3 should be greater than 29. So I got 59 degrees as we expected. Okay, so that will be the second question. Okay, now let's move into the third question. I mean second question, sorry. A beam of light is traveling through the media A and speed is given at media A. Speed at media A is 2.25 times 10 to the power 8 meters per second, and strike the medium B at incident angle as 45. So this is theta incident is equal 45 degrees as on the figure. If the refracted angle of the light is 30 degrees, theta 2 or 1, it doesn't matter, let's write 2, and that will be 30 degrees. What is the speed of the light in the media B? Find this, right? So now how we are connect velocity, because that's the definition of the refractive index. So now let's write the Snell's law first. NA sine of theta incident is equal NB sine of theta 2, right? So now N is basically speed of light divided by speed of media. So A, that will be A. For B, that will be B, right? So NB is equal C over VB, right? Let's plug that into here, then you will be able to calculate the VB. So NA equals C over VA, and sine of theta instead, I'm going to write the values at the same time. 45 equal NB is C over VB sine of 30 degrees, right? So sine of 30 degrees will be just 1, and sine of 45 will be 1 over root 2. Now I'm going to write another one in here. So, and same time I'm going to cross multiply. So I have VB sine 45 is 1 over root 2 should be equal VA times sine 30 is half, right? Then VB will be, see that you have VA times root 2 over root 2 over 2. So this will be equal to VA over root 2. So now VB will be 2.25 times 10 to the 8 divided by root 2, and that will give you the value of VB. So that will be 1.5 10 to the power 8. So now what you understand in here, the media B refractive index seems to be greater when the refractive index is greater than the refractive index of media A. That means the speed of the media B of the light is smaller than the speed of the light on the media A. Okay, okay, that's good. And now let's move into the question number 3. In question number 3, an object placed 180 in front of the convex mirror. So those informations are important for the question. Okay, convex mirror image with the magnification M. What happened to the image when the object moved 150 closer to the mirror? Calculate image position, magnification, orientation, and draw the diagram. Okay, so now convex mirror, whenever you know that convex mirror, F is a negative. So this means F is negative basically. Okay, F is negative. Why F is negative? Because if you have a mirror like this, then if you keep the object here, your center or the focal point going to stay at these places. That is your inside the mirror, that is virtual. That is why it is negative. Okay. Okay, so now let's do the calculation first. According to given information, in first case, D naught is 180 centimeters. Don't convert into meters here because everything you may use centimeters or you can use meters. You just spend in your time doing conversion. That is not needed in here. Okay, so D naught is 180 and also M is given 0.1, and then we need to find the F first, right? Let's find the F first. Why I need to find the F? Because second time I move the image into 150 from the location, that means 150 closer to the mirror. In second times your D naught going to be 180 minus 150, that means 30 centimeters. Okay, so then we need to calculate the information about the image, but before doing anything else, I know I need to calculate the focal point from the first one, if I can, right? So now, can I calculate the focal point? I don't know the focal point here. I even don't know the DI here, right? But you remember that the magnification will be able to write by using negative DI over D naught. Since I know the D naught and M, I will be able to calculate the DI from this first. DI will be negative M times D naught. Okay, so now you can calculate that. So then we calculate it, negative 0.1 times 180. That will give you DI equal 18, negative 18 centimeters, right? As soon as you calculate the DI, you can go to the mirror formula. DI plus 1 over D naught equal 1 over F, right? So now I can calculate the F. Now I have negative 1 over 18 plus 1 over 180 equal 1 over F. Okay, so calculate the F from this, and I get the F equal negative 20 centimeters. So that is correct, because since I have convex mirror, I can see my F is negative, surely. Okay, so now we're going to move into the second case. In second case, you are still going to use the same mirror, negative 20 centimeters. But you're going to change the object position. Now it's asking what will be the location of the image, what will be the image position, magnification, and orientation, right? We need to find everything for that part. Okay, so now let's calculate the DI first for the new case. Now new case 1 over D naught plus 1 over DI equal 1 over F, and 1 over 30 plus 1 over DI equal negative 1 over 20. Do the calculation and find the DI. So I'm just going to write the number here. What I get is negative 12 centimeters. Okay, that is one information the question is asking. Image position, right? And then I need to find the magnification. How do I find the magnification? Will be negative di over d naught. So now in this case, negative will give you 12 divided by d naught is 30. So that will give me positive magnification. Positive magnification number is 0.4. So it is not magnify, but it's shrink, right? So now I have all the information, image position, magnification, and orientation. So this will say, will create virtual image. Virtual, and this will say image is upright, not inverted, upright, upright, and smaller in size. Okay, smaller in size. Those are the properties that you found from those calculations, right? So now it's asking draw the ray diagram and locate the image and prove that your things you calculate is correct. Okay, so we're going to do it for one of them. Okay, we're going to do for the second part. Okay, so now drawing the ray diagram is very important thing. You need to draw your mirror first, right? Let's draw the mirror, convex mirror, and then you need to draw your optical axis, right? So you're going to draw the optical axis. You have the ruler, you can use it. So it's very hard to draw it on the screen, right? So this point is the point that will coincide with the mirror and the your optical axis. Whenever you label the optical axis, then you know that you, according to your calculation, your focal point is 20 and d naught is 30, right? So let's, I cannot draw the 20 centimeters, but I can estimate it. We'll say I have center somewhere here, right? So that means double of the focal point, that is basically 40. And this is where that I'm going to label it as my focal point. That is around 20 centimeters. So now object, you're going to keep it at 30, right? 30 means you need to keep it 20 here, maybe another part here, estimation, right? So let's estimate it. Or if you have ruler, you can measure it. Okay, measure it and rescale it, something like that. This is your object, right? So now drawing ray diagram, you know that you learn actually 4 rays, 4 mirrors. You only need 2 of them. Whichever 2 you like, you can draw it, right? You don't want to draw all of 4 because it will make your diagram is not clear, right? This is your center, this is your other center. Okay, so now whichever one you like, you can use it, right? So I'm going to use 2 rays that we discuss as one that will go through the focal point. If I can send this light to the focal point, right? Let's say I'm going to use red color. If I can send this light to the focal point from the tip point, but this is not real light, it will be reflect back from that point. How it going to be reflect back, right? So it hit on that point, but it going to reflect back from the that point, as we know that that should be just a give me a second. I'm not able to take that in my ruler, so it's very hard to draw. Okay, so I sent the light to the focal point. That light should be reflect back by making your reflection law. That means it will go parallel to the axis, right? So I'm going to draw it parallel to the axis in here, reflection. Okay, so that's the way that you learn, but let me draw it in here. I'm going to extend this one. This is extended light. There is no real lighting. So now this is my first ray, arrow in, and out, right? So now second one you can draw. Maybe I will draw the center one, right? So if you send light to the center, like this, right? So that light should be reflect back exactly same angle from the center. So I'm just going to estimate it. It's not exactly I can do exact the angle without the protector. So I'm going to just estimate it and then extend this light to here. And this is the reflection that you will see. Now, if you keep the eye, this eye going to see this red light and this blue light, incoming light towards the eye. So these two going to be overlapped somewhere in here, right? So now that is the location of your image. So now you see that these all are virtual because of that. Those are dotted line, not solid lines. Solid lines we use for the real light. This is the virtual image and you can label it as image. And also now if you measure the distance from here to here, that is your DI, you see that DI is less than 20, so it is 12, so it should be around 12. And you have upright image, smaller in size. You can also measure the size if you draw it to the scales. That means everything you have done in here is correct. Okay, so that will be your question number 3. And now we're going to move into the question number 4. Question number 4 is a concave mirror, right? So now there is a concave mirror and twice the size of the object. If the object is 20 centimeters from the mirror, what is the radius of the curvature mirror? Calculate image. Okay, so now we need some information in here. So what is given? So it is given your D naught is, read the question very carefully, D naught is 20 centimeters. In addition to that, you say that the magnification is twice, it says, right? But it did not say twice the size of the image. It did not say it is a positive or negative. I don't know it is positive or negative. That's right. Don't know which one is correct yet, right? And then what I need to find is R. Find the R means I need to find the F first. Right? So now let's say what we know from the magnification. Magnification is equal to negative DI over D naught. Right? So now if I use the magnification as positive, you're going to get the DI as virtual. Right? So now if I use the M is negative, then DI going to be positive, right? So now, but you see that here, what it's saying? It will create the real image. What that means? This means is DI should be a positive value, should be a positive value, right? DI had to be positive. To have a DI positive, M should be negative. Now you have conclusion. From these two, I need to get the M is a negative 2 because otherwise your DI will not be positive, right? So now let's plug that in here. Calculate the DI. DI equal M times D naught. So that will be 2 times negative, 2 times negative will cancel out. 2 times D naught is 20. And then you're going to get the DI equal 40 centimeters. Okay, so but that's not what it's asking. It's asking about the it's asking the calculate image location also. Calculate image location will be this one. Image location. And now I need to find the radius first. To do that, I need to find the focal point first. 1 over DI plus 1 over D naught equal 1 over F. And 1 over 40 plus 1 over 20 equal 1 over F. And you're going to calculate the F from this. And your F will be equal to F will be equal to 40 over 3, right? Yeah, so we have F equal 40 over 3 centimeters. That means radius will be equal to twice of F, right? So that means 80 over 3. It will be around, I'm going to write around 27 centimeters. That is the radius. Okay. So now I need to find the image orientation also. Image orientation, you don't want any calculation here because your image orientation is explaining by using this information. Image orientation is what? It is a negative now. Negative means it is inverted. We found all the information theoretically. So now I need to draw the ray diagram. Let's draw the ray diagram for concave mirror. Okay, so you have concave mirror like this. And then draw the optical axis, right? So as soon as you draw the optical axis, you can label your F. F is 40 over 3, 27 divided by F is R is 27. We'll say I have center here, 27, and half of that is F. That will be somewhere here. So now our DI is sitting 40 centimeters. I need to extend this one because this is 27. I will probably change these two dots little to the left. Okay, so I'm going to extend this drawing optical axis, right? Let's do here R, and here is my F. FC, and then I have 27, 40. That means somewhere here is my object. Estimation object is there, right? So now I need to draw the ray diagram, right? So you're going to choose any two rays that you have and then find the location of the image. Okay, so now let's draw whichever rays that you like to draw. So let's draw the your first ray. So I'm going to probably, it's difficult to draw it. I'm going to take the blue, and first ray I'm going to draw will be my straight light. So that will be reflect back through the focal point, right? So through the focal point, I'm going to draw this line here, right? This is the reflection. And the other one I can use the same ray that I have drawn for convex mirror earlier, right? Go to the center and to draw the line to the center, and that light should be reflect back exactly with the same angle, right? So oops, I'm sorry, so that's wrong actually. That's not 40 is not the D naught, so I think I did the mistake in there. Okay, so let's draw the ray diagram to locate the image, right? So let's draw it to a concave mirror here, right? And then you're going to draw your optical axis, right? Optical axis like this. Can extend it if I want. Say I'm going to extend it, right? So now you can estimate it. You see that your R is 27. Let's say this is your focal point. Let's say this is your center, and then your D naught as given, it is 20. 20 means it's basically a little away from your focal point. That means 20 will say this somewhere here, right? So that is the object. right? Now you're going to draw two rays, whichever two rays you like. Let's say I'm going to draw my first one parallel to the axis, right? Should be reflect back through the focal point. Let's draw that in here. Reflect back through the focal point. If you have rulers, make sure that you use the rulers because it's very hard to get the drawing correct if you do not use the uh, ruler, because you should have a straight line for the rays. That is my first ray. And let's draw the second one, exactly same ray that we have drawn for the convex mirror. So you're going to send the light to the center, right? And then that going to be reflect with the same angle, right? Same angle. Same angle. Same angle here. Same angle with incident, right? So now this is where that you're going to keep your eye, and this is where they will intersect. This is the point that you started, right? That tip point will stay in here now. Your image will be located somewhere here. Oh, sorry, image. Right? So now inverted, correct. Your DI positive, yes, because it is real. And 40, if you measure the distance from here to here, that will be around 40 centimeters, right? So now these things seems to be correct. What you find is inverted image, larger in size, and real image. Those are the information that you found from the calculation and also from the drawing. Okay, so now let's move into the question number 5. Okay, question number 5. There is two objects sitting in different places, right? So two objects, 24 centimeter apart in front of the converging lens, both produce the image 3 times the size of the object. So image size is 3. Don't know positive or negative yet, but 3 times the image. What can you say about the object's distance informations? Okay, so now what it says is you have converging cartoon, converging lens, and you have two location of the object, location 1 and location 2. They will create the image. This is 24 centimeters. That means the gap between these two objects, right? And then it's saying your magnification is 3. So now we need to think by using magnification 3 in both cases. For M1 also 3, M2 also 3. Magnification from first lens also, first object is also 3, second object also 3, right? So now let's think about this. Magnification will be able to write by using negative D. I am going to write 1 for the 1, 2 for the 2. Okay? D not 1. So now what I know, let's say this distance is X. Okay, because X is not given, right? So now DI will be something that I still don't know, I1, divided by D naught for the first one will be X plus 24. I'm going to do it probably different colors. So now let's do it for the M2. So M2 also negative DI2, but for the M2 now distance will be X, right? So now from this, I know that I can write DI2 equal M2 times X, right? It is also negative, M2 is 3 and X. From this one, I will be able to write I will be able to write di1 is equal 3 times x plus 24. Again, it is negative or positive, but I need to decide in both cases. I cannot have the both positive 3 for the your magnification. Why is that? You remember that how the converging lens work. Converging lens has the when the object is inside the focal point, it will create the image in this side in larger in size. And also the other one will create the image in larger in size, maybe inverted in the other side, right? So then whichever I have further away from the image, so that further away from the object, that may create the real image because it is the same, your lights are real in that case, right? So because of that only possibility, the object sitting on 2 create a virtual image in this side, and object 1 sitting on one place will create the real image. Because of that, I'm going to write, you have a di in here, will take m as negative, then you have this number is positive, because I need the positive answer in this part. Okay. So now I have these two informations. So now let's write your mirror formula. So I have 1 over d naught, right? D naught is x plus 24 plus 1 over di, that is 3x plus 24 is equal to 1 over f. That is for the first case. So now for the second case also I can do the same. I can write 1 over x minus 1 over 3x equal 1 over f. Okay, so now these two, you see that you right side are equal to each other. They are equal, right? Because you are using same lens. They are equal. Okay, so now since they are equal, I will be able to find the x. Let's do that calculation here. I'm not going to do whole calculation, but I will write the formula here. You're going to calculate it. Plus 1 over 3x plus 3 times 4 is 12. 3 times 2 is 6, and 72 equal 1 over x minus 1 over 3x. Okay, so do the calculation by putting everything into x value or by multiplying by common denominator and those things. What I found is you need little more steps in here. So you do it, and I get 24 centimeters as x. Okay. So now after you find the x, how do I find the f? So easiest way is go to this formula in here. So 1 over x minus 1 over 3x equal 1 over f, and then plug the value 24 into here. Minus 1 over 24 times 3 is 72 equal 1 over f, and you will be able to find the f from this. What I have is 36 centimeters. Okay. Let's see, we give the answers to all the questions. What can you say about the object distance, image locations, and orientation? So object distance, you see that after you find the x, your first one is x plus 24, second one is just x. And image location, for the first one, your image location will be after you add the x number 24 into here, you can calculate the d1i, and 3 times x will be your d2i. So location, good. And orientation. Orientation is the magnification. So that means my first location of the object will create a magnification, negative magnification, because it will create the inverted image, and M2 magnification will create a upright image. Because of that, it is a positive number. So you can summarize it, you can find it as a simple example, what you need to do is you need to write DO1. DO1 is, you see that it is 24 plus x, right? 24 plus x. Since x is 24, that will be 48 centimeters. And DI1 is equal 3 times x plus 24. That means 48 times 3. That means 24, 12, 144 centimeters. And then do the same magnification in here is M1 is -3. That information is for the your first lens. Okay, this is for the first one. And you do for the second lens. Second lens D02 is equal to x, right? X will be 24 in this case. And then DI2 is -3x. -3 times 24 is 72 centimeters. And M2 is +3. Those will be the information for the second position of the object. Okay, so you can draw probably one of that. You don't want to draw all of them. Draw the ray diagram for the one object. Let's do it for the second object, because second object is the trickier one. Okay, let's draw the ray diagram for the second object. No, I have enough space. I'm going to draw probably small image in here. You have converging lens. I'm going to do for the second one. So we have optical axis, right? And so now I know the focal point is 36, right? So 36, we have two focal points in here. Let's label it small distance, 36, 36. So that will be my focal point. This will be twice of the focal point, C. And this is the important focal point for converging lens, right? So now image, the object will be 24 centimeters. From that, 24 centimeters is less than 36. That means your object will be, we'll say somewhere here. That is the location of the object. So now we're going to draw the ray diagram. So first one, we're going to do parallel to the axis. Make sure that you draw your vertical axis first. Always for when you are drawing it for the lenses, you should have that line. And then we're going to draw your rays. Let's use one of them. So one of them will be sending light parallel to the axis that will go through the your focal point on this side. Okay, that is one. And in addition to that, you can draw the center one. Center one is directly go through the center. So let me extend this light to the other side. This will be virtual. Okay, so now let's use different color. For the second ray, I am going to go through the center one. Go through the center. I'll go to the center like this, and that also I need to extend a little bit. Right, this way, go like this. This is where you're going to keep the eye, and then you're going to see your image created. This intersection point, that is little away what we are expecting, but you create the image in somewhere here. That is virtual image as you expected, and it is invert the upright as you expected, and it is around 72. If you measure this one from here to here, if I draw it to the scale, that will be 72. Okay, that's how you do the ray diagram. So I hope this is nice. Okay, I have two more questions. Let's do this one. So now question number 4, you have informations about your height, right? So tall light, you have H naught is given 4 centimeters. and place the left from the concave mirror. So you have D naught is given as 45.7 concave mirror and the focal length of 15. Concave mirror focal length is positive 15.2 centimeters. Okay. So now determine the image distance, image size, and orientation by analytical method first, and then by using free diagram. And so now this one, we know that we can write 1 over di plus 1 over d naught equal 1 over f. So I am going to plug the values 1 over di plus 1 over 45.7 equal 1 over 15.2. That will give you the value of di, that is the location of the image. So that will be 22.8. Okay, so now what I need to calculate is magnification. So magnification equal negative di over d naught. So that will be negative 22.8 divided by 45.7. That will give me the magnification as 0.5, negative 0.5. That's the magnification. And since it's asking the image size, right, orientation, I can write it because since it is negative, it should be inverted. And orientation, the image size I can write because magnification also equal to hi over h naught. Then I can calculate the hi from this. That will be m times h naught. So that will be negative 0.5 times 4. So that will give me the hi value as 2. Okay, that has negative value, right? So that will be centimeters again. Okay, so now I have all the information for that. Now it's asking me to draw the ray diagram. So let's draw it for the concave mirror. So I'm going to do it here. I'm going to draw a small drawing in here by using small scale. So concave mirror, right? So now object distance is 45 and focal point is 15.2. That will be almost 3 times of that. So let's say I have focal point somewhere here. Then your image location, estimation somewhere here. I mean object location somewhere here, right? And then you need to find the image location by drawing any 3 rays that you like. Okay, so let's draw the first one. I'm going to send the light parallel to the axis. That should go through the focal point. So it will be reflect back through the focal point. And then going to choose the different ray, maybe the center one, maybe the going through the focal point I choose, going through the focal point. That also should be parallel to the axis. So now I found the image tip point somewhere here, right? And then you're going to draw your image location in here. So now you see it is inverted. And if you measure the distance, will be 22.8 and object size, almost half of the size of the object. Image size is half of the object size, almost the same, right? So now use the convex mirror instead and repeat the process. I will leave it for you to do. If you have any question, you can ask. Okay. Okay, so number 7 is the last one. Okay, so we're going to do it for the diverging lens, right? So divergent and convergent lenses, both again, I will do one of that. Okay. So now there is an insect at 100 centimeter in front of the diverging lens. Divergent lens means focal point is negative, right? That you need to keep it in mind. So let's write the information given. So you see that D naught is given. D naught is 100 centimeters. And focal length is given. As soon as you see it is divergent, you need to write negative yourself, 25 centimeters. Let's get rid of the suffix and do it without that. 25, right? So now what I need to find, image location, magnification, and image orientation again. So we're going to use your mirror formula, lens formula or mirror formula, di equal 1 over f, and that means 1 over 100 plus 1 over di going to be equal to negative 1 over 25. You can find di from this. What I have is, for this is negative 20 centimeters. That will be the location of the image. That is virtual, as we expected, as always for the diverging lens. And then magnification is negative di over d naught. So that will be negative, negative will cancel out. 20 divided by d naught is 100, right? So that will give me m equal 0.2. So it is smaller in size, as we always expected. As we expected, it is upright. What do you find? We found upright image, upright. We found smaller in size image, and we found virtual image. These three things are always true for your diverging lens and also convex mirrors, right? So I'm going to draw the diagram for this one, right? Because we did not do any drawing for the diverging lens in your worksheet. So let's do it in here. Diverging lens, you draw in like this, right? And so as always, you draw your optical axis first, and then you need to draw your vertical axis, right? So now you need to label your focal points. I have one focal point here, here, and focal point here, and here center. Focal distance is 25, right? So, yeah, so I think I should label it a little closer because object seems to be 100. So let's label focal point here, F, and focal point here, F, and C is double here. And your image object is sitting 4 times of that, 100 centimeters away. That means this is where your object is, right? So now you're going to choose 2 rays and draw it, right? First one is, you're going to draw parallel to the axis, right? So that should be refract, diverge from the focal point. You have it in here. Make sure that you label this focal point. That's easier to remember. This will be diverge like this, but I'm going to extend this light into this side also. So this is first ray, right? So second one, you can draw to the center one, right? So center one is easier for the lenses always. So let's draw the center one and center ray like this. So this should go through the center, okay, although it did not. So I can probably erase it and draw one more time. So go through the center, it's important. So now you are watching in this side, you see the red and the green. So now you see the connection in the intersection of these two will happen in here. So that's where you're going to see your image. See, very smaller in size, virtual, and upright. That information is correct. So now do it for the converging lens yourself. You can ask me if you have any questions. Okay, so let's stop here.